Um, what I would like to talk about is GNU Radio. So what Ben showed you is OpenWebRX, which is nice in that it is a complete package. But basically what it provides is a series of canned modules that does different kind of things. What GNU Radio allows you to do is to actually build your own SDR without having to write a bunch of C or Python code. So the key thing about GNU Radio is that it's software, right? The idea is that there are a number of modules which you can think of as either functions or modules that talk to each other and interconnect to each other. And you can take all of the different modules, such as getting the RF stream, demodulate the audio, amplify the audio, and things like that, and put them all together, and then build a radio out of those blocks. So it works kind of the same way as in Linux or Unix, where you take the output from one command and pipe it to another command and pipe that to another command and basically do whatever processing that you want in each of those commands and then do it well. What GNU Radio basically does is to have these streams between the different modules that then put everything together. The key thing is at the end, you end up with a program, and that program reads from your hardware and outputs to your audio device, or takes your microphone in, does whatever manipulation it does, and finally gets it to your transmitter and then gets it to use. So it is software. The nice thing about GNU Radio specifically is that there is something called GNU Radio Comparison or Companion, also called GRC, that gives you a nice graphical interface on how to actually put this all together, which makes life a lot easier. So it's truly just drag and drop. You don't have to be a programmer in order to be able to do it, but you can do very complex things. Because it is software, of course, it is very processor intensive. So it's a good idea to have a fairly fast computer to actually run that. I happen to like the i7 series processors from Intel, and they have plenty of computing power. However, this also will run on a Raspberry Pi. A Pi 3 is barely fast enough to keep everything up. So Pi 4s would be preferred if you can do that at all. And for those of us, Ben, that are truly geeks and love math, you can actually write your own modules and then add it to GNU Radio. So you extend it. So specifically, what's nice about this is that it's extremely powerful. You can basically build whatever kind of hardware, radio you want. It supports a whole wide range of hardware. What I'm going to demonstrate is just the cheapest one, which is the $20 Nuelec RTL SDR, but it also works with the $400 HEC RF, which is sort of the geekiest of all of those devices, or some of the more professional hardware from other commercial vendors. Because it is open source software, of course, it runs on all platforms. I'll show you how to do this on Linux, but it works just as well on Windows or Mac OS. And then, the fact that you have GNU Radio Companion to actually just do the drag and drop, put everything together, makes life really easy. Here's a demonstration that I just grabbed off of the website of what GNU Radio Companion looks like. So you'll see there are all these different boxes. So in particular, we have the source box here that you have a bunch of parameters associated with. And then you'll see there's a little blue box next to it. That's the output from this. And the fact that it's blue indicates that it's an IQ stream. So it's actually a complex data stream, which is a convenient mathematical way of representing basically two streams of data that gives you, that we describe as the real and imaginary components. That then gets filled into a resampler, which basically just is a way of changing the rate at which the data comes out. that goes into a low pass filter, that goes into a wideband receive. And then in the wideband receive, it goes from blue to red. So when it goes to that red or orange color, that then becomes a real signal. So you've got a complex signal coming in, it demodulates that, and what you have is coming out is just an actual, like a real signal, like an audio analog signal that you can then run through other things. So there's another resampler and a multiplier and stuff like that. But then you finally get back down to an audio sync. So a lot of complexity there. But the key things to remember here is that you need to match colors. So the blue means that it's an IQ stream, and the different data sinks and sources, you need to go from complex to complex. And basically what that means is that the type of data is compatible. And then if you're in the real world, those connectors are all orange. And again, there you have to go from type to type. And then you'll find a few gray connectors, which is where they want you to put in either a string or a number or something like that. That's more like a control. The biggest thing to make sure that you get right is that the rates need to match, right? So in addition to the type of data, if this puts out 2 million samples per second, the receiver need to expect 2 million samples per second, right? So you need to make sure that you don't do time dilation where you're feeding it more data than the other guy is expecting, in which case it'll drag it out and it'll sound like Donald Duck. Or if the receiver expects a faster data rate, then it won't have enough data. So it'll sort of stutter, right? It'll use the data that it has, wait till there's more data, and then go on again. So that's the most important thing to get right. So I'll show you how to actually use this, but of course we need to get the software installed first. So if you're on an Ubuntu box, it's really easy. All you have to do is a sudo apt-get install, and there's two things that you need to install. The first is the GNU Radio software itself, which basically gives you all of the core components, all of the things that all of those modules that you need to run. But it doesn't give you very good support for hardware. So the best source for hardware is from this website, Osmo SDR. And specifically for the RTL SDR, if you install GR being the abbreviation for GNU Radio, Osmo SDR, it'll give you the hardware modules you need to actually interface with the actual hardware that you need to do. If you are going to directly connect to that device using USB, it's also a good idea to install the latest and greatest RTL SDR modules. And I'll go into the detail of that on the next slide. There are actually default RTL SDR modules in your regular GNU distribution or your Ubuntu or whatever other distribution you use. But it's not it's better to just reinstall it with the latest data. And so the way that you do that is you do an install of CMake, package configure, and libUSB, which it's just prerequisites that you're going to need to actually build this from source. And then you just get cloned from the Osmocom site, the RTL SDR repository. And then you just go through these commands, which is well documented on that site, to actually just rebuild those latest drivers from source. And what it will actually do is it will blacklist the existing drivers so that they don't get used, and then replace them with the newest set of drivers. And then they'll also set up some UDEF rules, which is the Linux way of figuring out what hardware is there and waking up the right software modules at the right time to get everything going. So once you've got that installed, you're actually ready to build your first receiver. So what I would recommend you do is you start with some commercial broadcast station, just because they have a nice strong signal that's there all the time. and you can use that to debug what you're building. So in my case, the KYGO 98.5 transmitter is about 4 miles from my house. So I've got a nice strong signal and I can actually receive that. So that 4-component receiver that I built there is actually the easiest way to get started. So what you're seeing here is actually the GNU Radio companion interface. So it has all of the usual control boxes up here at the top. And then each of these boxes that you see here are the different modules that you're going to need to actually build the receiver. Then there's also this options box where you set things like what's the name of the file, what's this thing called, and so forth. Then to run it, there's this green play button here that if you click that, it'll actually play whatever you're going to have. Now, the room that we're in here is a Faraday cage. So if I try to receive anything here, I'm not going to receive anything. So what I've instead done is I've grabbed this little module, right? This is one of those Bluetooth plugins that you just plug into your cigarette lighter. And it actually picks up Bluetooth signals from my phone and then retransmits it in the FM band. And I've tuned this to 98.5, so I don't have to rebuild my software here. And it'll just play whatever music I play from my phone. So I'll play some music from my phone here that everybody who listens to KYGO will have an utter heart attack when they hear this. But still, it's a way of getting a signal from an FM signal that I can then receive with my RTL SDR. So the RTL SDR here is connected to an antenna. This is just a screw-on SMA connector. It's hard to do this without an opposable thumb. It's just a regular RTL SMA connector that goes right on top of it. It's a nice metal enclosure, so it's somewhat protected from very local transmitters. And then the bottom end of it is just a USB connector that I don't want to pull out here, but it's just a short USB extension cable that plug directly into my radio. And this is what I'm going to use to actually build the whole system. So what we need to do is we start with a new interface. So you do file new, and no GUI means the radio doesn't have any controls. So it's just a command line. And it will give you this variable box here, which I'm not going to use. So I'll click on it and then just hit the delete key to get rid of it. And then I'm going to go over here on the right-hand side, and I'm going to select Osmo SDR and double click on the RTL SDR source. And what it will do is it'll pop up this box, which if I then click on it again, it says, okay, now you need to configure this box. Tell me what you need. So there's 3 tabs up here at the top. The advanced we rarely have to use. The general we will use all the time, and then I'll show you documentation in a minute. So the first thing is the device arguments. If you leave the device arguments completely blank, it'll just look on your USB bus for a suitable device and then grab that, right? So in this case, I only have the one RTL SDR to connect it to this. So if I just leave that string completely blank, it'll actually go and find it. Most of this other stuff I just leave alone. The next thing that I need to set is the sample rate. Now, Ben already talked about that. What's the appropriate sample rate that you use for what device? Well, for these, I'm going to use 2 million samples per second. You can push it a little harder if you want to, but I just want to listen to one station. So 2 million samples per second is plenty. And then you have to tell it what frequency you're going to use, right? So in this case, 98.5 megahertz, I put in as 98.5 E6, right? E6 being the scientific notation for a million. So you specify that frequency in hertz. So 98.5 E6 is 98.5 megahertz. And all of the rest there, you can just leave whatever it is. The key thing is that what that box will now do is it will go to the RTL SDR, it'll tune it to the frequency that you asked it to tune to, and it will start sampling that and push out of the other side of the box 2 million samples per second in IQ notation. If you want to know what else you can do with this, go over to the documentation tab. The documentation tab either shows you the documentation here, or it will give you a link to the website where that particular module is described. So in this case, there's actually quite a bit of information here. Most of those just point you to the actual wiki that says, okay, it takes these parameters and this is what they do. What I wanted to point out in this case is that I am actually sampling directly off of that hardware through the USB. But what I could have done is put this device on a Raspberry Pi and put it somewhere close to the antenna. And then use a program called RTL TCP, which comes with the RTL package that you built. And it basically takes the USB signals, converts it to a TCP stream, and all you have to do is to say, hey, go connect to that TCP stream and then start snarfing that data in. So if you wanted to do that, you would say in the device field, which I left blank, you would say RTL TCP, you would give it an IP address and a port number. So that then says, go get the data there, and it'll basically do all of the controls, tuning it, and setting the rate that you want to get the data out, and then pull it out. However, as you can see, there's all kinds of other things that you can do. So if you had a HEC RF or an AirSpy or any of the other kinds of devices, you can actually tell it about the device itself, or if it's a remote device that you access over Ethernet, explain to it how you do that. The long and the short of it is that RTL SDR module is extremely flexible and is the one that we use almost for all of the devices to actually start snarfing that data in. So basically what we have now is we have this 2 megasample per second that's coming in. But what I want to do is now tune it down to a band that is just wide enough so that I can actually receive that station. So what I'm going to do is to pass this through a low pass filter. So I would go on the right-hand side to core filters, low pass filter, and it'll give me a new box with blue tabs on both sides. So it takes an IQ signal in and an IQ signal out. And I'm going to say, this is what I want you to do. So the input rate is going to be 2 million samples per second, right? I put that in here as this is the sample rate, and that has to match what the output of the last one was. And then I'm going to do decimation. So in the signal processing world, we have two terms, decimation and interpolation. Decimation means you're making the samples fewer. Interpolation means you're making the samples more. So decimation 4 basically means that every 4 input samples you turn into 1 output sample. If you do interpolation, it's the other way. So if your interpolation is 4, every input sample now gets turned into 4 output samples. So well, it's actually for the interpolation, it's truly being interpolated, right? So you have a value, and you fill it in. For decimation, typically you would average them so that you get the effective value of the last 4. So in this case, because I'm doing decimation 4, I'm getting 2 million samples in. I've got 500,000 samples per second going out. And then I need to tell it what my cutoff frequency is. So I'm listening to broadcast radio. So I'll say, oh, let's call it 100 kilohertz. So I put in 100 E3, which is then, of course, the cutoff frequency. And there's other things you can set, but not that important.
Well, why wouldn't you do it?
So it is effectively a bandpass because we're sampling around a center frequency. So SDR has this really weird concept of negative frequencies. So what I essentially want is I want a bunch of frequencies around 0. So a low pass is basically setting up that I want these frequencies around 0 as opposed to what it's really doing, which is a band pass, but it's taking the original center frequency of the SDR and then doing plus or minus 250 actually, right? So it's really a band pass around 98.5, but it's a low pass around 0. Does that make sense? It's really weird in the SDR world. It's just, they have these weird concepts, and it's it's a low pass around the center frequency that of 0, which is actually an offset from the real frequency. So it's really a band pass. It's, you have to, yes.
Well, I just had a quick question. You said you were using the mathematical E's. I think you said E6 and E4 or something.
Right.
E2. Will it recognize if you put it in as megahertz, or can you have it set so that it'll
You
do
just
that?
have to put enough zeros there.
Oh,
It doesn't
okay.
take, it wants a numerical value, right? So if you want megahertz, you have to say, add 6 zeros to the number.
Okay, that's why I would just want to make sure
Right,
that that
right.
was possible.
You'll see in the output, it actually sort of summarizes that for you. So if you look at this, you'll notice that it reports it here as 6 capital M or 2 capital M, I beg your pardon, right, which is basically 2 million. No, well, so if you put in 2M, it's an integer with a value of 2 million. If you want a floating point value, which is what it needs, you need to put it in as E6. It cares about integers and floats. So that was the low pass filter, which is really a band pass filter. And then, so the output here is 500 kilohertz. Now what we need to do is demodulate it. So if you go to core modulators, there's a whole bunch of modulators for all different kinds of systems. And the one we're going to want to choose here is wideband FM. Right now, wideband isn't what HAM's called wideband. This is broadcast wideband, right? Which is, what is it, 200 kilohertz or something like that. So you put in the input frequency or the input rate, and it calls that the quadrature rate. So that again needs to match the output from the last filter. And then we want to set, okay, what speed is the output at? And you set that by setting the audio decimation. So since we're coming in at 500, if I decimate by 20, then the output rate is 25,000. So the big difference here is that you're getting IQ data in, but you're getting real data out, right? So you're now back in more the analog or the digital analog world. And then finally, what I need is I need to play the audio. So the easiest one to use there is just the audio sync. So you would go core audio sync, and you have to tell it the input sample rate, and you don't have to tell it anything else because it's going to look for the default output device and just play it as your system audio. In this case, it'll actually be ELSA audio, and voila, it's going to work. Except for one thing, you still have to connect up all of the modules, right? So what you're actually going to do is each of these modules we've created, we've set their properties, but now we have to connect them all together. So you simply click on the output tab and drag it over to the input tab, and it'll basically find the nearest spot and connect all of these up. And if I connect all of these three, everything will come together in feeding the data through that stream. If you get this little red button here showing up, the thing that looks like a don't enter sign, what that means is you've got something wrong in your connections. So you're feeding a kind of data out that doesn't go into the data in. And if you click on that, it will tell you what exactly it's unhappy about. Otherwise, what you can do is you can click that green button, which basically says play, and strictly speaking, it'll actually generate that audio. So unless I screwed something up, I can hopefully show you how that works. So here is GNU Radio Companion, and I actually pulled up that exact system that I just demonstrated. So if I click on any of these, you'll see that I have all of those parameters that I just showed you as the different values. So there's the low pass filter, there's the wideband FM receive, and there's the audio sync. What I'll do is I'll just break one of those connections and then just reconnect it just to show you how that's done. So you just grab it and you drag it over, and that all connects it. And if I now hit play, you should be hearing the music that I'm playing off of my phone. No, it's not KYT. Well, let me play something else for you if you really are. Oh, come on. Hopefully your extension strikes better. So what you'll see down here in the lower hand box, it basically shows you just that it's running. There's a data stream going. And of course, it's just syncing to audio. So if I would go to my ELSA mixer, I can actually go in here and control the volume and turn it up and down and do all of the regular stuff that we do with ELSA, right? So the output from this here, we think of it as analog, but it's really PCM audio, right? Which, we can turn into analog audio at any time. So the nice thing about all of this, of course, is that I can, control this in whatever way I want. I can set in different frequencies. If I want to tune to a different channel, I would simply go and put in the different channel here and so forth, right? So you can basically build your whole radio. Now, of course, this is just a piece of software. So what I can actually do with this is I can click on this button here, which is build this. And what it will do is you'll see it saved to a file here called GNU Radio kygo.py. So in my options box, I select what kind of output I want to have and what the name of the file is. And it will simply go and generate this program for me that is now a Python program. If I go to that particular program, come on, give me the box. You'll see that kygo.py exists here as a Python program that just pulls in all of these various modules that I've just created here, and I can run it from the command line like any other program. And the music will start playing again, right? So the nice setup here is that you can either do this with Python or you can select the C++ program, which you will then have to recompile. But you can basically create a custom program to listen to a particular station and play whatever you want to play. So this is by far the easiest way to start because it's a FM broadcast system, right? It's out there transmitting all the time and it's good for playing around and debugging and so forth. However, we're hams. We want to listen to stuff in the ham band, right? So let's see what it takes to actually do anything in the ham band. This is what I just showed you. So let's build a narrowband FM receiver, right? Something we can use in the ham band. I'm going to tune this to 146550. The first thing I'm going to do is to reduce the sampling rate because I want to listen to one channel, right? That channel is, call it 20 kilohertz wide. I don't need to sample the entire 2-meter band. So I'm going to reduce the RTL SDR sampling rate to 1 million samples per second. And you can see right here, what I've done is I just clicked on this, changed the sample rate to 1 million samples per second. But then, of course, my low pass filter also needs to update it to say, hey, I'm now receiving at a different rate. So I would click on that. I would change the input sample rate to 1 million. And I changed the decimation to 10. Because instead of getting a 500 kilohertz signal into my demodulator, doing narrowband FM, right? 100,000 samples per second is going to be plenty. So I'm going to change my decimation rate to 10. So I'm going from 1 million down to 100,000. And then I'm simply going to delete the wideband demodulator and add in instead a narrowband demodulator to actually do that. Well, the narrowband demodulator is even simpler than the wideband one. All I have to do is I have to tell it the quadrature rate, what's the rate that it comes in, which is now 100,000, set the audio still to 25,000. And notice that this thinks differently, right? It asks you what's the input rate and what's the output rate, and it figures out the decimation for itself, right? It's just this guy that wrote this particular module, that's how he thought. The FM wideband says, tell me the input rate, tell me the decimation, and that will determine the output rate. So what as you use these different modules, some of them are going to do different things than others, and you're just going to have to figure out which specific one that you want to set there. It also gives you a deviation setting here, right? Because for wideband receive, that wasn't one of the options, but here I'm actually going to turn down the deviation a little bit. So that, if I have a limited range of modulation on my transmitter, it'll still come out here at a decent rate. The default is actually 5 kilohertz, but set it to whatever you need to do. Of course, the other thing is that once I start this up, I'm just going to have a bunch of squelch noise there all the time, unless somebody transmits all the time. So what I actually want to do is also add a squelch control. So the squelch control is going to be added in between the low pass filter and the narrowband receive module. And what this simply does is it looks to see if there's a signal coming in. And if there's a signal that's stronger than whatever level I set, it'll actually open the squelch. Otherwise, it essentially just cuts off the signal. So there's my squelch module. I went to core level controllers, simple squelch, and said, I want to do squelch. Notice that there's no speed or anything like that set. It figures that out for itself. All I have to do is to set the squelch threshold. And I experimented here with this, and -30 seems to be appropriate for my setting here. And the cool thing is that the input and the output rate is all unchanged, and it figures out that for itself. So let's give that a shot. So where is my GNU Radio? What I can do here is to go file open and say, oh, I want a new receiver. Well, it's the narrowband FM that I want to use. Well, let's turn that on. And theoretically, so my lovely assistant, Deg, actually keys up and gives us a transmission.
Good morning, Willem.
We have to identify that's transmission.
0KQ, WB0EBA.
So you can hear that the squelch is not quite perfect. It has sort of this at the beginning and at the end. Well, I mean, essentially what it's doing is it's cutting off the signal and re-enabling the signal, right? So it's doesn't quite get the K2AD seal of approval in terms of audio quality. But you know, the long and the short of it is that it actually senses that there is a signal and then basically start it basically just sends zeros because you can't shut off the signal altogether, right? But if you just send zeros all the time, then that's essentially interpreted as, well, there's nothing going on. So it'll basically just stop playing that. And again, in addition to being able to look at it here on the screen, I can, of course, save that package. Actually, it's still running. By the way, that's the play button, that's the stop button. It'll just keep on playing. Of course, since there's no transmission, you don't hear anything, but it actually is running in the background. And I can similarly, from the command line here, go and run that narrowband FM Python script. And I just saved it as Python scripts because if you save the Python script, you can actually take that script. And if you have a Raspberry Pi somewhere, just copy that Python script there. The Pi also already has the Python script or Python interpreter installed. And you do have to have the GNU Radio modules installed, but it'll then basically go and run that code. If you run this or use the C++ module instead, then you have to compile for a particular architecture. So if I compile it on this x86 machine, that will only run on x86 machines. If I want to run that on my Raspberry Pi, I have to move the source code over to my Raspberry Pi, recompile it for the ARM processor, but it will still run. What actually happens at a lower level in GNU Radio is it's all C or C++ code, right? So from an efficiency point of view, it really doesn't matter whether you run it as a Python script or a C++ script at the command line level, because all of the hard work happens in C++ anyway. But if you really care about that last 1% of efficiency, you can do it using C++ instead. So obviously building any kind of radio there is actually fairly straightforward. However, what you'll notice was all of these were very, one time, right? Listening to one channel kind of programs. So what we really want to do is add some controls to it so we can actually make this look more like a real radio. So what I've done here with the wideband receiver is to simply add a few more controls to it so that I can now actually set things directly. So specifically what I want to be able to do is to set the frequency and the volume, and then add a waterfall display and a spectrum display to actually see what the signals look like. So what I've added here are a few new modules. So the waterfall module basically just splits the output from the RTL SDR, and it basically runs the same output as goes to the LPAS filter also into the waterfall. And I just need to configure the waterfall to show me what that looks like. Similarly here at the end of the receive, I simply put what they call a histogram sync, but it's basically just a spectrum analyzer that'll show you the spectrum of the data that comes out of there. And then finally, what I did was to install in between the FM output and the audio sync a multiplier. So you have to think about this all mathematically, right? Your data stream is just a series of numbers that are coming out. If you want to increase the volume, you just want to make those numbers all bigger, right? So what you do is you just multiply them all by a constant, right? If you multiply them by 2, you're going to increase the energy by 2 in that signal, or if you multiply by a half, you're going to reduce it by a half. So that's all the multiplier does, is it just makes the signal bigger or smaller, and essentially amplify or attenuate it by just multiplying it. So the first thing I want to do is to set up the frequency control. This is really easy to do because all we're going to do is to replace the numbers that we had before by variables. And then there is a control that allows you to set the value for that variable. Now, you don't have to actually associate that with a control. You can actually set variable names as just something that you sent once. But in this case, what I actually did was I created something called a GUI range. So you go to core GUI widgets, Qt GUI range, and this will give you a slider. So I tell it that slider is called frequency or FREQ. That's the name of the variable. You want to add a label to it because we forget. So in this case, we're going to say we're going to label the frequency. The type of this variable is a float, and this is the range of that float. So that's the start value and the stop value. That's like the minimum and the maximum. This is the step. So we go from 88 to 108 megahertz. This is the broadcast band, of course, in 100 kilohertz increments. And the default value I set to 98.5, just so that that's the default value that comes up when I start the program. And the widget type is a counter and a slider. So basically what that will do is it'll give us a slider that we can use to change the frequency, as well as a spin box that we could use to actually set the value. And then in our RTL SDR source, all we have to do is where we used to have a number here that said 98.5 E6, we just put in the name of the variable, which is the same as the variable here, and we have a control. The next thing that I then want to do, why do I have that in there twice? Sorry. The next thing I want to do is to control the volume. So I'm going to have another Qt GUI range, and I'm going to call that volume. Its values is going to go from 0 to 100 by steps of 5, but I changed the widget type to a knob just to show you what it looks like. And then in the multiplier, I just said, okay, this is what I want you to do with this number. This is a trick that we often use. So I make the knob go from 0 to 100, but I really want the number between 0 and 1. So I don't have to put just a variable in there. I can actually put an expression. So I'm taking my number between the 0 and 100, multiplied by 0.01, and that basically changes the number into a number between 0 and 1. To create the waterfall, all I do is I go to core instrumentation, Qt GUI waterfall sync. And the only thing that I really have to set here is the bandwidth. So basically what this will do is to look at the numbers that comes out of it. And this sort of addresses the question about why the hell do we use a low pass filter, not a band pass filter? Your values are all relative to that center frequency that you've tuned your RTL SDR to. So if we put a bandwidth of 500 kilohertz here, it's basically going to go 250 kilohertz above and below that center frequency. So it either confuses you more or it solves the problem. And then finally, the histogram display. Basically, the spectrum, we do the same thing, except this deals with a bunch of floats. And you just tell it how many points you want to have and how it's actually going to divide that up. And if I were to actually then run it, this is the result I'm going to get. So it'll actually create a new GUI that will pop up and say, hey, if you want to change the volume, there's a knob to change the volume. If you want to change the frequency, here's a slider that you can move left to right. I've set the range to 88 to 108. So 98.5 is right in the middle. And I can actually set the number here by clicking the up or down arrows or just typing in the frequency there. It will actually put in the number. If I were cleverer, I would have multiplied the result that I put in by 1,000,000 and made this go from 88 to 108. But I only just thought of that solution rather than yesterday when I was making the slides. And then the output from the waterfall is shown here. You can kind of see that there's actually a station being received, and there's some sidebands there as well. Of course, again, this is time 0 and time goes back there. So this particular range is 20 seconds. And then here's the output from the audio that then shows us the actual data. And again, this works both from the command line as well as from the actual GUI. So let me pull up that last one here. It called Fancy. And notice that it's just what I just showed you. And if I were to hit play, let me change the song just so you can hear. You'll like the music better. Play Stars and Stripes again, just because everybody better like that song. So you can kind of see here's the spectrum. That's really the only signal that I have in this room. You can see the actual audiogram here of the frequency spectrum, and I can change the volume. Basically turn it up or down. I can, of course, change the channel, and then you'll just hear noise. Oh, there's actually something there. I don't know what I'm receiving there. And there we're back on channel. So obviously you can kind of see how the waterfall was trying to follow us around. Again, maybe that makes the whole center frequency thing a little bit clearer. But basically, you know, fairly elementary controls, but you know, this is a roll your own. So if you want more fancy, you may actually have to get down into the source code level to actually play with this a little bit more. So basically what this does is it just multiplies whatever stream of data by a number. I've limited that number to 0 and 1. So my maximum volume doesn't increase. I can just make it softer. If I wanted to increase the volume, I would put in another multiplier that multiplies it by 2, and then I can reduce it, right? So this particular control, I mean, if I go in here and just change this to 2, then it'll just be twice as loud. Well, not twice as loud, but twice as much power. Come on, play. Right, so now it's just. It's a mathematical multiplier, right? So the numbers are twice as big, so it should be 3 dB, yes. It would be voltage, so it wouldn't be power, right? You're right. So you'll have to do 4 in order to get twice the power, right? But it'll distort, so I won't do that. And of course, I could also just run it from the command line here, which will then behave the same as the others, except that it will pop up the control for me, so I can actually have this control here to, oh, sorry, I saved it, so my volume control doesn't work anymore. I have to go back and fix the volume control, but you understand the principle. Okay, so that's about all I have the time for, but the thing to remember is that, well, you have to put Shift F5, and I forgot to put the F5 in, the Shift. So there are lots more possibilities. So if I had more time, I would actually go into this a little bit, but this is how you actually would set up a transmitter. So you basically just reverse the process, right? You start with your audio source. This multiply constant here will change what your drive power is. You've got a narrowband FM transmit, which you then have a signal source here to actually give you your CTSS tone. You would pass it through another low pass filter here. and then you would put it into something that would then turn this into RF eventually. But so, you know, the possibilities are essentially endless. It just gets a little more complicated on the transmit side, just to make sure that you don't have spurious emissions and things like that, that will get you into trouble. So this is all software, right? So you're going to need to do one of two things. Either you have to do that decoding in software, or you have to have an interface to a piece of hardware that'll send that stream there, do whatever ambi decoding it needs to be done, and then bring it back. I don't recall seeing
Can you
that.
just pipe it though from, you know, for like one of those decoders that Ben had showed?
Right. So if you actually look at this here, let's look at the modulators. I didn't, so you wouldn't do it in the modulator, right? You would first demodulate it, and then you would run it through something that takes that digital signal and then turn it into whatever non-signal it is. So that's probably somewhere else in one of those 26 million menus that you don't want me to go through and look for it. But I mean, it's all just a digital stream that comes out, and you all you need to do is to take the stream that you get out of DMR and figure out what those, you know, signals mean, and then turn it back into a PCM stream that you can then treat as regular audio. The long and the short of it is everything that you ever wanted to know is on one of those two pages, www.gnuradio.org, and the wiki has lots of excellent examples, tutorials, how-tos, things like that, that will help you get all of the standard stuff figured out pretty easily. And if it's hard to do, it'll tell you where else to go look to do the hard stuff. So very, very, very fine piece of software, very proud of what people have done as far as the open source community.
Your RTL, but like with the SDR that John has or hack RF, is there different drivers that you've got to load? I know you pointed us and said, hey, these are the RTL drivers.
Right. So the RTL SDR is the one that I use because it supports pretty much everything. Sorry, get it up here again. So if you actually go down here to this driver here, actually, I can just look at it right here. If you look at the documentation, it basically says it'll do the RTL. It'll do the RTL as a remote TCP. It'll do SDR play, all of the RF space devices, the AirSpy, the hack RF. This ETIS is just a variation of the RTL SDR. And, you know, there's probably better complete documentation on the Osmo website. But this is the one that I use for pretty much all of the hardware that I have. Do you have any other ideas of other drivers to use here? Right. But this is the one that works for everything that I have. Any other questions? Great. Well, let's take 5 to get John set up here, and we'll talk about the next topic.